So I want to go through all that once the long way, and the other ones I'll just write it down, you know. But you can go on making similar arguments, adding planes of symmetry. So if you have 3 orthogonal planes of symmetry, then you have additionally those terms equal to 0, and you have 9 independent constants. This is called an orthotropic material. If there exists an axis about which a material has identical properties, then you have 5 independent constants. So you can imagine if you have a material and there's an axis, say x3 in this case, about which if I rotate any way around that axis, if I take the sample and I rotate it any arbitrary direction around that axis and do the test, and I always get the same properties, right? So a good example of this, anybody know what this is called? It's called transversely, there's just one L, transversely isotropic. So a good example of this would be like a composite material. So if you had, say, a material that was a sandwich of, you know, hard and soft layers in the plane, something like this, right? So if I pull on it in the plane, no matter how I rotate it, I would always get the same behavior. But if I try to bend it out of plane, or pull on it out of plane rather, then it's going to be a different set of material properties that characterize that. And so you need 5 independent constants to characterize a material like this. And this is starting to get to engineering type materials here, obviously. I mean, all rocks are some sort of composite, right? But if they're laid up in a sedimentary way, then a lot of times you get this sort of transversely isotropic